Good afternoon, everybody. Today, we have the pleasure of hosting our own Ido Kaminer. Ido Kaminer graduated from the Technion, did his PhD under Moti Segev, distinguished Professor Moti Segev, and he went for a postdoc to MIT. And I'm not sure I'm daring to pronounce the name of his advisor there. I think it's Soljacic, but I probably mispronounce it, Indianopoulos. And he came back to the Technion recently and built his own lab. And he is very nicely decorated for, and we are proud of our new recruitment as a young faculty to the Technion. You can see for yourself, he has an ERC grant. He has been awarded the Azrieli Foundation and scholarship and many other honors. And recently he published a paper that made a reasonable amount of splash. You could even read about it in Haaretz, Physical Review, I think it is called. And today he will describe to us this work, and I think the work done in his lab. So before I pass the floor to Ido Kaminer, I would like to say that since there is a substantial crowd in this meeting, participating in this talk, over 60 people, I request that those of you who have questions, please send them to me by chat. And we shall see if how to, and I shall handle the questions. Some of them I'll transfer to the speaker during the talk. Some of them will be deferred to the end of the talk. So Ido Kaminer, the floor is yours.
Thanks, thanks Yossi. I hope everyone can hear me okay. I'm really glad for the opportunity to present the work that my group did at the Technion in the last few years. We are running for about 2.5 years now, and the lab is running for almost 2 years since we started installing it, so a bit more than a year since we finished. We have some really exciting stuff happening also these days, and it's a lot of fun to do. I'm really glad for the invitation for the seminars, especially I think to be one of the first speakers in the seminars of the Dealer Center. I really hope that we will be able to create and also sustain a strong tradition of those seminars, even during Corona times. We already had some really superb speakers in the quantum colloquia. That was also before the Corona era started, with really important people that came here and significant discussions that came from that. And I hope we'll be able to bring this back to create more collaborations, also between groups in Technion and outside in all of Israel. I hope that despite this being a Zoom talk, you'll feel free to ask questions wherever. Also, some of them want to talk. So please feel free to do this, even if it's less personal when it's in Zoom. What I wanted to talk about is our work about free electrons and free electron physics, and specifically both theory and experiments that we did in this area. Before I start with that, I want to say that our group these days is working on several areas. I'll not have time to talk about everything, of course. We have some interest in X-ray sources. That is an area that is also related very tightly to free electrons as the way to give the energy for those sources. Also looking into ultrafast detectors, especially into what are called scintillators. We're doing some work on nonlinear optics, extremely nonlinear optics, which is areas that connect to harmonic generation, and specifically how to apply strong field quantum electrodynamics to model such effects, and how to find quantum statistics phenomena of light in nonlinear optics, and especially in the very strong field regimes of it. And we're also applying what is called microscopic quantum electrodynamics, or MQED, and especially in areas of 2D materials. Now, when coming to prepare the seminar for today, I was actually trying to decide between between two sides, two topics that I had a lot of opportunities to discuss also with people at the Technion in physics and in electrical engineering. One is on the areas of collapse of free electron wave functions during the emission and absorption of light. This is an area that we do both theory and experiments in. I gave a colloquium on this in Bar Ilan that also led to some really interesting collaborations. And I want to, but eventually I thought, since the Helen Diller is not just about quantum, it's also about quantum technology and trying to look into certain areas of quantum that are now more modern, then I went to another direction. And I'll focus this seminar on one topic that I think is very, very exciting for our group these days. And this is our journey after the quantum nature of the Cherenkov effect and what applications of free electron physics it can lead to in accelerators and in radiation sources. So I'll talk about this, and I'll start on purpose from talking a little bit about the Cherenkov effect. I think it's a very good way to give a flashlight into this field. This is a really a funny photo, because when I show it in the seminars, typically people can recognize one of the two figures here. But then that one is normally the left figure, the one who is awarding the prize, of course, the King of Sweden. But the right figure here is the scientist that got the Nobel Prize back then in 1958. That's Cherenkov, who did in his PhD the discovery that we now call the Cherenkov effect, and with his advisor Vavilov. And the Cherenkov effect is a phenomena that's created when a charged particle is surpassing the speed of light in the medium. This is analogous to what happens when a particle that emits sound waves is surpassing the speed of sound. And then, let's say, a jet plane moving faster than sound is creating those shock waves that's causing the sound waves to interfere with one another. And when they interfere this way, since it's moving faster than them, they can create a shock front that will propagate and carry this, what we call here as a sonic boom. And the same kind of phenomena happens when a charged particle surpasses the speed of light. It will do that, of course, only when it's moving in the medium, and we have nuclear reactors submerged in water. This is exactly what's happening. We have charged particle emitting from there, and they are moving faster than the speed of light in water. And that allows them to emit radiation in those shockwave dynamics. And that's what we call the Cherenkov radiation. And it's very well characterized by this cone. You can see here how when a particle moving through a medium of index n, the radiation will be following a cone symmetric around the particle with angle theta. And the relation between the index and the angle will follow this very simple formula, that what we call the Cherenkov angle for sine theta is equal to c over v dot n. So it depends only on the index of refraction of the medium and the velocity of the particle. And this phenomena is what we understand as the Cherenkov effect. Now, it's actually one way to understand it, especially for people coming from areas of optics and nonlinear optics, is that as a result of phase matching of the electron with the light. You can really think about the electron as matching its phase dynamics with the phase velocity of the light wave, and that results into a strong interaction that causes radiation to be emitted. And we will see later how this can be really understood through as a phase matching results. Now, the Cherenkov effect is something that we now see in a lot of different areas. In physics, it's used as a detector of high-energy particles coming through the atmosphere. That's how one of the major mechanisms by which we can actually tell information about particles coming from outer space. There was until recently a Cherenkov detector in the International Space Station, and there are many Cherenkov detectors in high-energy physics detectors. But in all of those scenarios, we always think about the Cherenkov effect as something classical. We think about the particles, electrons or others, as classical point particles that are flying with a fixed amount of velocity or momentum, and it's moving through some medium, can be the atmosphere, or it can be some body of water or another even solid, and then emitting radiation into that medium. And one question that I was pursuing for a long time is, where does the classical description break? And so far, there were no experiments showing any quantum features of the Cherenkov effect. And the first thing I want to talk about today is the first such experiment that we did here at the Technion recently. So a little bit about the history from my side, what really brought me into this effect. I actually started working on this around the time I moved from my PhD here at the Technion to MIT. This was my first project at MIT. that was looking into the effects of what are the quantum corrections to the Cherenkov effect. And it led us to a series of theoretical papers that we wrote at MIT. And they were all related to this question of, if we have an electron that is not just a point particle, but it's some more complicated wave function, how is the Cherenkov radiation going to change because of that? And some of you may remember that my job talk at the time was actually also about this topic. And I want to show you that a lot happened since then, especially that we were able to measure some results coming from this. But I want to show one slide from my job talk back there, because I think it's giving an interesting context that this effect has quite a long history of exploring the Cherenkov effect, and actually from a quantum perspective. And the first person to do that was Ginzburg, who did his PhD on the topic in 1940. He was the first quantum analysis of the Cherenkov effect. And even back in the same year, also in Russia, was Sokolov that also did it in a relativistic quantum electrodynamics approach. And so this is quite old, the approach of looking at what quantum mechanical approach can deal with the Cherenkov effect. I really like this quotation. This is a paper that Ginzburg wrote in 1996, so it's 56 years after his PhD ended. And here he actually said how negligible the quantum corrections are. And he even said in 1940, when Landau was told about my work, he stated that it was of no interest. And I always found it quite amazing to think what a PhD student would say when Landau said something like this to him. And he agreed later on, and also talked about it later in his life, that it follows from the above that he was fully justified in drawing this conclusion. And his comment hit the mark, as was usual with his criticism. So really the consensus for many years about the Cherenkov effect was that it is quantum corrections for it will be negligible. And I think it's fun to see that so many things changed in how we think about physics, and also in how we can do experiments of very high precision, that now we can actually look into features of that scale and not neglect them anymore, and actually find that they can be quite significant. And I think this is interesting to think about a Cherenkov effect, but there is something more general here. And it is saying something about any process of phase-matched interaction. Any process where we bring two particles, can be an electron and a photon, and match their phase velocities so they interact in the most efficient way possible. And so I want to bring one slide that is more general. It's more of a big picture of what are the kind of quantum effects that happen that we can think about when talking about phase match interactions of the type of the Cherenkov effect. Those interactions also appear in electron accelerators, for example, or in a lot of other in traveling wave tubes, in older types of radiation sources based on electrons in our microwave at home. And what kind of quantum effects can happen there? There are three types of quantum effects that we can see. The first one, and it is also the one that Ginzburg studied back in 1940, is the result of the quantization of the electromagnetic field. When a particle is emitting a wave, we should think about this wave as being quantized. And that means that the particle is not really emitting energy in a gradual way, but in a discrete way. So the momentum of that particle, for example, has to recoil in discrete quanta. And that's first seen in the context of the Cherenkov effect, theoretically. And it is called causing recoil corrections. So it's related to other phenomena in physics, like radiation reaction. The second type of quantum effect that we can think about, this general picture of electron-photon interactions, is not when the photon is treated as quantized, but when the emitter, here the electron, is treated as quantized. So if we think about the wave nature of the electron, it can arise, for example, from transverse features of the wave function. Like if we think about the orbital angular momentum, so the electron carries some spin. This is a phenomena I was studying back then in 2016 paper. It can also arise from longitudinal features in the wave function. And there are actual series of papers on this, on the temporal profile. For example, there is a paper from Nahit Halevi, who's a researcher in Germany. There are several very interesting papers by Avi Gover and Yiming Pan, who's his postdoc, that appeared over the last couple of years, looking into how is it really the structure of the wave function in the longitudinal direction altering the radiation. And there are some interesting consequences there. And generally, when we think about this interaction without phase matching, so we think about any type of interaction of electron and photon, these effects are related to what we call PNEM, and I will talk about this later on. Those are just really a key phenomenon in the microscope. So I'll keep this acronym for now hidden, and we'll go back to this. And the third type of a quantum effect that can happen for electron and light interacting will be higher order processes. scenarios where the higher order diagrams are significant. For example, the electron can emit a photon and then reabsorbs the same photon, and that normally requires stronger coupling, which is not easy to get in free space, but I think we're getting pretty close to that. So if I summarize this slide, so far none of this was observed. And I'm glad to say that we observed one. We actually can claim for the observation of the second type, where the electron quantum nature is significant. And how to do this is what I'm going to talk about in the next couple of slides. So what we were looking into as the one of the earliest experiments we ran in the lab we built with Technion is the observation of the quantum nature of the Cherenkov effect. And for this, I want to bring back this formula of what is the Cherenkov angle when we emit radiation from a particle moving in a medium, and suggest why not look at the reverse effect. And this is the work that was led experimentally by Rafael Dahan, who is a lab engineer in the group, and designed even before we started the experiment by Sarah Nehemia, who is a master's student in the group. Now, what we thought to do here is to make the Cherenkov effect in reverse. We bring light to couple into the electron at the angle that is exactly the Cherenkov angle. The way to do this in practice is to use a big prism. That prism has the light coming from top. That light is then coming at a right angle to the electron. It's totally internal reflected. It does total internal reflection from the edge of the prism, and it's reflected back. And then through this interaction, we can show that fitting the right angle, we get a strong transfer of the energy of the laser light into the electron, so it can actually accelerate it, or it can cause stimulated emission, then even slow down the electron. Both effects are going to happen. Both absorption, that's the inverse Cherenkov, and also emission, additional emission of light, that's stimulated emission of Cherenkov radiation. And now that kind of setup is actually inspired by work by the Homelov group in Germany, where they did this completely in a classical picture. We actually can see how quantum effects are happening here, also measure new kind of phenomena there. I'll talk about how this is happening in the next few slides. So first, what is the key challenge if we want to do this kind of thing? It sounds, on the face of it, pretty simple. We have a prism, we bring the electron next to the edge of the prism, we bring a laser at the right angle, and all of that interacts perfectly. So the number one challenge is to actually match the electron to graze the surface. Because if you ask, the electron cannot really penetrate through the glass like we would like to do in a regular Cherenkov setup, mostly because it just collides and is lost too quickly. So what we do instead is we bring it on the edge of the glass, right on the edge, so it feels this, it senses the field, and it still interacts with the Cherenkov conditions, but it only senses the field that is evanescently decaying outside of the glass. We said total internal reflection, and that means there is an evanescent tail of light that is extending to a scale that is on the order of a single wavelength. And that means the electron has to pass on a distance that is smaller than the wavelength of light over a length that is several hundred of times, actually about 1,000 times the wavelength of light. So this ratio of 1 in 1,000 means that the alignment has to be very precise. And such an interaction with such conditions was never achieved in electron microscopes, for example, like what we show here. The first achievement of that in a transmission electron microscope is what we really did here. That was really the key experimental challenge, achieving the grazing angle interaction that will be following the electron along this long line. Now, where is this actually happening? So if I put this entire setup, it actually happens in this kind of experimental setup. This is what we call the ultra-fast transmission electron microscope. It's in the very essence of it, a tip that is illuminated by one pulse, the UV pulse, emitting an electron. That electron is accelerated to up to 70% speed of light. In our case, we ran with this energy, and on another pulse that is creating the interaction in the prism. And then we take those electrons after the interaction, and we send them into an electron energy spectrometer. This means we tilt them by 90 degrees with magnetic field, and they split by velocities. And that split allows us to tell apart different energies that the electron are carrying with this. So this is what we call the ultra-fast transmission electron microscope, or the UTEM. And the rest of the experiments I'll talk about today are all happening in this setup. I'll talk later on a bit more about what kind of lasers we use and stuff like that. But first, what I think is the most exciting part about this experiment is what is really the role of the electron wave function that's happening inside. And For this, we should compare two scenarios. If I zoom in on the area of the interaction, we have this laser pulse that is reaching to the edge and is doing total internal reflection and flying back. And we have the electron pulse that is flying by. And we should compare two scenarios. If we think about an electron as a point particle, it will do one kind of interaction. If we think about it as a wave function, it is an extended wave function, it will do a very different type of interaction. And we can see that when the velocity of the electron is exactly matched with the phase velocity of light, an interesting thing happened. If I look at those points here, the point of the electron arrival, if it was really a point charge, would be exactly matched with the phase of the laser. So it sees the field pointing one way, and as it moves by, the field is moving exactly the same velocity, so the force is exactly the same one. And that electron is going to either accumulate more energy, or if it comes to the wrong phase, it's actually going to be slowed down in a most significant way. Now, what happens to the wave function? The wave function actually is interacting at the same time with both the peaks and the dips of the electromagnetic field. So it sees part of the same electron that is extended, sees the strongest field pulling it down, and the strongest field to the other direction, pushing it actually back up. And those effects are actually happening at the same time. So we have the same electron that is interacting in a meshed way. Parts of the same electron are accelerated very strongly, and parts are decelerated very strongly. And then the way this then behaves, if we look then at the electron energy spectrum, so we look at what is the electron energy spread, and this is the difference between the original energy, this is what we call zero here, and the new energy we measure, we see this spread of energies that is having this periodic oscillation in behavior. And that means that the electron is actually, same electron is absorbing or emitting, depends whether it's positive or negative, a significant number of photons. The difference between the peaks here is exactly the energy of the photon. There is another way to understand this entire experiment, and we can think about it as an analog of a double slit experiment. If we think in space, what happens to a wave that passes two slits or more, then goes on the screen, we see those fringes appearing there. So one can think about this experiment as a double slit experiment happening in time domain. The wave function is interacting with a field that is periodic in time, and that gives us a periodicity in energy instead. And those two pictures, one of them is of an interference pattern in energy and time, and one of them is absorbing and emitting a discrete number of photons, are exactly equivalent. And we will see more of the theory on this. But before I go into the spectrum more, I want to say one thing about the phase matching. The condition when we bring the electron exactly at the right velocity relative to the velocity of the wave. So this phase matching condition is what it is when it doesn't happen. We say the phase mismatched. We can see that the particle, the same particle, if it was a point particle, would see at some point in the motion a field pointing up, and then suddenly a field pointing down, or the other way around. And the same will happen for an extended wave function. Different parts of the electron will feel fields that will cancel out. And that's how, when we don't bring it exactly the right velocity, we very quickly see that the acceleration diminishes significantly. And we can see this, for example, if the energy of the electron is exactly 207.2 keV, we see some spread in energy. And when the energy is slightly shifted from this, let's say by 1 keV, we see a significantly smaller spread in energy. So the interaction is much weaker. Okay, and now if I try to explain what is really the essence of the interaction here. So the experiment we do is what we see here. But to understand the experiment in more details, I want to take a look at the bigger picture of this. What is really the intrinsic interaction of the electron and the light? So I'm going to plot it the following way. If we have an electron passing by and some electromagnetic field, I'll not describe it exactly. I'll just say it is described by some E of RNT and B of RNT. And we want to describe this electron interaction and how it changes it in its energy. There could be different ways of thinking about it. Since I told you wave functions, you may think one way, but if I bring this to a high school student, he will say, well, if I want to see how the energy of the electron changes, I can look at the forces I learned about in high school. There is the electric force and the magnetic force, which together constitute the Lorentz force. Right? The Lorentz force is QE plus QV cross V. That tells us how much force is applied on the electron. And if we want then to integrate along the dynamics of the electron, that's maybe a little bit beyond high school, but still will be first year undergrad, we can find how much of the energy of the electron changed. And for example, if I took then an electron of a certain energy distribution, let's say around 120 keV, it will do some shift. It will shift itself, let's say, to higher energy if it comes at the right time. So that's the classical picture. That's what we will expect to see experimentally if we do this experiment classically, but it's not what we see in the lab. What we see in the lab is a spectrum that looks like this. And I actually took the spectrum from a Nature paper by the Rocco's group that came out in 2015, and you can see this discrete series of peaks that appear there. And those are exactly separated by the energy of the photon. And that is the quantum behavior. That the first thing that is quantum here is, of course, that the energy is not a single value. There are multiple options. And that is part of what we understand now as a result of the Schrödinger equation. And the theory for this fits experiments amazingly well. If we write the Schrödinger equation and then apply the fields, classical fields, so we change the derivatives in time and in space by putting in the scalar and vector potential, we write a new way of, like a new form of the Schrödinger equation, that when we solve it, we can really get the exact dynamics of the wave function and eventually find those discrete peaks happening here. And I'll show this in a couple of slides. I just want to say that the first paper to see this dynamics, before even understanding the theory that's happening there, was by Ahmed Zewel in Hotech. That was a 2009 paper, and that's, since then we are actually coining this name and looking for this effect. And I think that when seeing this work and the follow-up work like by the Rocco's group, it's really opened our eyes for a lot of us in working on electron experiments, and also classical electron experiments, because it was a hint for quantum effects that happens with free electrons. And now people can ask, well, where else? Can we see those kinds of effects in synchrotrons, in free electron lasers? Can we find quantum effects in old style traveling wave tubes in microwave ovens? Where does the quantum physics of free electrons can change the things we do for many years in the community? There are more papers with those thoughts, especially by Peter Baum, that also wrote several interesting comparisons between the classical and quantum description of the same effects. And I want them to take one slide to explain what happens when we take the Schrödinger equation and go through the derivation to see what is going to happen there. And the hint for what to look for is that we're going to see that the description of this electron that started as a Schrödinger equation, so it's partial differential equation, can end up being described as a ladder of energies. This ladder of energies is very similar to thinking about a Fouquet physics problem. And the way we call this effect, and I said this word before and I promise I'll go back to it, is the photon-induced near-field electron microscopy, or PNEM. Photon-induced near-field electron microscopy is a term named by Zewel, who was doing chemistry and who was seeing this as an effect of microscopy technique, basically. For us, it's much more of the physics that is interesting here. So let me show you a bit of the theory that's happening here. If we started then with the Schrödinger equation, and now put in the vector potential and the scalar potential, we get a PDE that we can simplify with a few approximations. The most important of them is the Praxel approximation. And since the electron is very energetic, it's very directional, we can neglect all the second derivatives. We can find an equation that will be a first order in both Z and T, and has an explicit time dependence. And we put here a monochromatic single frequency electromagnetic field. Now, that one actually has an analytic solution. And that was first done in parallel by Garcia de Abajo and Matthew Kosiak, and also by Sancté Park from the Zewel group. And what you do to solve an equation of that type, it's a first order but still time dependent, is a Fourier analysis, or what we call Fouquet. We split it into Fourier components, where each of those Fourier components is basically the amplitude of the electron being in a specific energy. And those components, we call them FLs, are the ones that are the decomposition of the field. And we can actually solve that analytically, find that FL can be written as some phase element times a Bessel function of order L, and with a parameter G. This G parameter, we call it the PNEM parameter, or the dimensionless interaction strength. It's an integral over the field along the direction of the electron. So we find that only the longitudinal part of the electric field alters the electron dynamics in the Praxel domain here. And the Fourier transform over it gives us a dimensionless parameter, which is really the amplitude of those Bessel functions. And this depicts the amplitudes of the electron when it spreads over the ladder in a coherent way. And then the probabilities, of course, are then going to be the module squares of those amplitudes. So that's the probability. That's exactly what we measure directly in the lab. One interesting remark about this derivation is that when my first PhD student started working on this was back when I was still coming back from MIT, He actually resisted using the theory as is and was really trying to derive this more generally. We talked about both the Dirac equation and the Klein-Bordern equation as the way to start, because you see the electron is actually relativistic in our system. So it sounds a bit funny to start from the Schrodinger equation. And when doing that properly, we actually found that there was a gamma factor wrong in all of the papers that were published on the topic. Actually, over the last year and a half, there were a series of errata papers coming out, fixing some of the older papers, because there was really a gamma factor wrong, and things fit better with this correction. So for students here, sometimes it sometimes pays off to be stubborn about stuff you do. So how do we look at the data in scenarios like this? We are looking at the spectrum of the electron. So we look at the electron energy after it interacts, and then the very simple experiments will typically look something like this. This is the energy of the electron and the electron counts. And we see the majority of the electron that did not do any kind of interaction. That's the original electron distribution. They had some width to their energy. And then we see two small peaks on the sides. And that will be the initial electron energy plus minus one photon being absorbed or emitted. And that can be seen also analytically from using the Bessel functions in the right way. When we increase the laser strength, what we find is that instead of seeing one peak on each side, we see multiple. The distance between them is still exactly one photon energy. And we see many, many multiples of the original photon energy. And that's the scenario that has for stronger laser energies. Now, one thing very interesting changes when we reach the phase matching condition of the electron wave and light wave. We bring them to interact in phase match condition. The strength of the interaction grows significantly, and the result qualitatively changes. And suddenly the energy looks something like this. You see that it's the same effect, but spread over many, many peaks of the electron energy. We can actually, we took this spectrum, we didn't feed the camera, so we had to do this multiple times, and that made the experiment much more complicated. When you can see how this actually spreads over a very wide range of energies. This is the electron gaining any discrete number of photons you like, from 0 to hundreds. And that is what we can really call a free electron energy comb. So there is a discrete set of peaks here. The electron becomes a comb. This comb in energy means it's also a comb in time. Fourier transforming it will mean it's actually a sub-attosecond or around 1 attosecond electron pulse duration. And this is one of the attractions that the community finds in doing those kinds of interactions. So we see this kind of data happening there, and we saw that this is happening over multiple, very wide range of energies. Our record with this experiment was a width of about 1700 electron volts in the comb what the electron is approaching. And with the more recent experiments, we did about double of that number. And we expect to be able to do much more than that with more advanced samples that we're discussing with colleagues. Also with, for example, Kobe Scheuer, that I think is also connected, that I saw connected before. So that's one type of thing that we can do that I think is really interesting here. Now I want to focus on just the first few peaks here, because I think there is one thing here that goes into the fundamentals of the interaction that is really interesting. If you think about what is the meaning of the electron that hits the camera at this location, this is the electron that didn't absorb or emit any photons. The electron that is on the right side of it is the electron that actually lost 1 h-bar omega of energy. So it emitted 1 photon. And that electron can be thought of as doing this kind of diagram. That electron absorbed 1 photon, or absorbed, but this is the very simple Feynman diagram for it. And on the other side, we have the electron that emitted photons. Sorry, that was the electron that absorbed the photon, and that is the electron that emits a photon, right? So anyway, up to a minus. And we have multiple orders of that as well, right? So if this is like plus h-bar omega of 5, so that gains 5 photons energy, and it goes on and on. And the diagrams that describe scenarios like this will, for example, be something of that type, a third order diagram in QED, so absorbing 3 photons. And when looking at those kinds of diagrams, and the first time I saw this was in conference when Klaus Roppers presented this in Austria, and that was very peculiar for me, because I thought, well, we see those diagrams, we can plot them, but when we learn in first year about interactions of that type, we actually think about them as forbidden, right? Those kinds of QED diagrams, even if we don't call them QED diagrams, they're considered not allowed to happen, because we can actually do this in first-year physics. We write the conservation of momentum and conservation of energy. Here I'm writing the initial momentum of the electron absorbing one photon, initial energy of the electron absorbing one photon, and those two equations, when combined with the dispersion of the electron and the dispersion of the photon, gives us exactly 4 equations with 4 unknowns. And we can just solve this and find that there is no solution to that kind of diagram. That's the first order here. You can see this graphically. This is an explanation that Levi Schechter showed me when I was an undergrad. How to think about the absorption and emission of electrons. You can do this in a, if you plot the hyperbola of the electron dispersion, this is the blue here, and then show the light lines underneath, then what will be the meaning of absorbing a photon? It will be an electron changing its energy from one location on the hyperbola to another location, doing something like this. But that process, if it's done by absorbing one photon, should be, the photon has to have exactly the energy and momentum of the difference here. But any photon will have to be exactly parallel to the light line. So there has to be a line that is parallel to the light line that connects those 2 points. And that's impossible. You can never find a line with the slope of the light line that connects 2 points of an hyperbola that is convex above the light line. So geometrically, this cannot be done. So what is really the reason that we still get that to happen? Because we plotted these diagrams and we show why it is impossible, but in practice, experimentally, it just happens, right? So, and that happens all the time in our experiments. So that's really the reason that we are allowing diagrams that are considered forbidden from conservation laws. So I think the reason for this, and if someone wants to interrupt me, can do that too, but, is that those interactions are not happening in complete free space. The electron is moving in free space, actually, in our experiment, but the photon isn't. The photon actually has a medium to modify it. This diagram is happening inside an optical environment. And for example, take the simplest case of that. The photon can be modified by the environment having an index of refraction. The index of refraction that I added in red here actually means that there is a change in the dispersion of the photon. And that change in dispersion of the photon is effectively like slowing down speed of light or like tilting the slope of the light cone. And that allows those transitions to suddenly occur. So one can think about the Cherenkov interaction in the most fundamental basic sense as just a regular first order diagram with the light being modified. And those kind of ways of changing QED diagrams can be extended to much more complex ideas. Not just in complete simple index of refraction and in much more in higher order phenomena as well. And that will be what we call MQED, or Microscopic Quantum Electrodynamics, which is the equivalent of taking Maxwell's equations into microscopic Maxwell equations that are when there is an environment, optical environment. But here instead, having the diagrams in QED change. And if someone wants to read more about this, it can be a full lecture as well. I'm giving a grad class on this topic. There is an excellent review from 2008 by Schill and Buchmann, and now we have one coming up in Nature Reviews Physics. That's already an archive that is talking about the theory of microscopic quantum electrodynamics and what it means for light matter interactions. So if I summarize this experiment, we have 2 ways of thinking about this interaction, and we have a third way, which is thinking about it as a classical Cherenkov effect, and we actually can explain the same thing in all 3 methods. And all of them can be equivalent to thinking about phase matching phenomena that we do in optics. So we get exactly the same thing. And I think this is an interesting trigger to understand this as a novel kind of optical nonlinearity. Because in a way, the electron is our medium here, and what we see is a phase change and then a frequency change for the photons that are equivalent to other kinds of optical nonlinearities. For example, the electron changing its energy in such a way is related to what is done in above threshold ionization, is causing harmonic generation to occur. And we now find that the same theory can actually apply to both here and also for the creation of harmonic generation. Now, what I want to talk about next, and for the latest part, last couple of minutes for the talk as well, is what happens when we also think about it without phase matching. But before this, I want to show you that this can do a couple of interesting things for us when we describe the theory for such interactions. And for that, For example, when we think about the electron, this is like a movie of the field dynamics.
Ido,
Yeah.
can I interrupt for a minute? Since you encouraged question from the audience, there was a question by Avraham Gover who would like to ask a question. So let's hope it is a quick one.
Can you hear us? Check that you're not muted first. Maybe I cannot see you, by the way.
Can you see me?
Yeah, I can hear you. Yeah.
Oh, just a small comment. You discussed what I call the relativistic, in quotation mark, Schrödinger equation, and I just want to make a small correction to the equation that you showed. You showed that all you have to do is replace the mass of the electron with gamma m. And in fact, it is a little bit more complicated than that. It turns out that indeed you don't have to use Dirac equation. You can use something that is like the Schrödinger equation. But there are two corrections for the interaction. The correction is for the interaction Hamiltonian. You really need to use only a factor gamma m. But for the zero order, it turns out to be gamma cubed times m.
Yeah, I think
I will not get into details, just refer you to a paper that Aaron Friedman and myself published already 30 years ago in Review of Modern Physics. And we also repeated this same development of the relativistic Schrödinger equation in a later paper of Iming Pan and myself, perhaps the one that you cited before.
Yeah, it's also in Ori's thesis proposal. You're absolutely right. The thing is that you can have a simple gamma factor and not a gamma cube if you work in the paraxial approximation. Under the paraxial approximation, you don't have the gamma cube make any difference. But if you actually take into account the three-dimensional behavior of the electron wave function, you'll need to do more than the gamma factor. That's since we are working practically, it works well. But that's because of that paraxial approximation. So you're right that in most general sense, it will not be that simple. Dirac cannot be ignored so easily.
It's actually simple, and it doesn't matter if it is Purcell or Cherenkov.
Let me interrupt. I'm sorry. I don't think we should have a discussion now on this issue. I would suggest that Ido continues.
Yeah, well, we can discuss this after. Anyway, to understand the behavior that we have here, as said that this is the paraxial regime of the interaction. We have the electron phase meshed with the field. It's a movie that's running on the screen. And what we saw that we need to do also to extend beyond the Pinham theory is when we write the wave function and go through the process, we actually find this is the G parameter that I described before, the Fourier transform in the field, actually has to take a more general form than what happened before. If the simple theory for Pinham actually took a field that was monochromatic, here the monochromaticity of the field is not enough. The group velocity of the field, for example, matters a lot. And what we find that happens here is that the motion of the electron through the field, so we actually have to integrate over this field in a way that is not a simple Fourier transform, gives us a time-dependent interaction strength. If we neglect that correction, we go back to the regular Pinham theory. And in that sense, this actually forced us to extend the theory in a way that was quite significant to what we got. Now, I'll just say quickly that from those expressions, we derived then a density matrix that gives us a density of the electrons, of the coherent electrons, that can be seen as the modulo square of those coefficients that are the amplitudes of the field times delta functions for the energy of the electrons. But we also know that the electron energy is not really that narrow. It's not really a delta function. So we need to convolve this with another density matrix that comes from the electron initial state. That's the rho naught here. That is giving us the density matrix of the original electron. And doing this additional convolution gives us the actual measurement. And that fits extremely well with the data. I'll show you one slide for how we look at this data in both the energy axis, which you see here, and also the time axis. So we delay the arrival time between the electron and the laser pulse, so we can actually test the interaction as a function of time, you see that for zero delay, the energy spread of the electron is very wide. This is the strongest possible interaction we get. And when we change that delay, the electron slips away from the laser, and then the interaction gets weaker and weaker until at the really wrong times, multiple picoseconds apart, that electron doesn't change its energy. It stays at the original energy it had. And when we cross through this, we see this is one example for a full spectrum at zero delay. So it's a very wide spectrum with a lot of discrete peaks there. And then when we match it to theory, and this is using the conventional opinion theory, we find that the actual theory doesn't fit the wide spectrum we're looking for. However, when we match it to the theory that is actually taking the dynamics into account, we get a much wider spectrum. And those fits actually convinced us that we need to find better ways to model this. It also had other features like the convexity of the plots here that suddenly fitted better. So we feel very confident that we have a much stronger theory here behind the scenes. And I think this is also what we are now trusting on when we design future experiments. So let me show you one example of such a future experiment. But before this one thing about what we are actually doing behind the scenes. So this is a photo from the lab where you can see the actual electron microscope where the interaction occurs. You can see the femtosecond laser system that's sitting on a floating optical breadboard, floating with the optics together. It goes around the system and then with some optics coupled into the electron microscope. We're using a laser system that is a 40 watt, 1 megahertz repetition rate, light conversion, carbide femtosecond system. And this is a Joule microscope. Combining those systems together is actually with the specs we chose is done for the first time in our lab. But I think what really makes it unique relative to other systems of that type or cousins is that we designed it to be very flexible in a lot of ways. And I think most important, and we had to do a lot of modifications for this to really make a custom system, is we wanted to be able to control the frequency of light to work in regimes of parameters that were never tried before. One of them is in the mid and far infrared, which we actually did some experiments recently, and this will be for another talk. The construction for this was in October 2018 for actually modifying the setup. Zero Feldahan, our lab engineer here, and since then a lot of stuff happened. I think it's really amazing to think of the super hard work that people in the group did since then, and some super exciting results we got, including a lot of interesting science, seeing photon polariton dynamics, and recently looking now into more physics, and I'll be glad to discuss this more. Some of the ideas that are jumping into our labs are also coming from collaborators, and it's one of the things I was really hoping for to see happening. So something about what was done in this field, to give some context. I told you about the Zewa work in 2009 and the theory that was done since then. And there is the work that for me was significant in having me hear about this was the Nature paper by the Ropos group that originally saw how you can think about the dynamics here as that one walk around along a ladder of energies and observing Rabi oscillations. Then the Carbonic group, which are our really good friends from EPFL, saw how you can use this system to image plasmons. You can see here standing wave plasmons on a nanowire. And I think a lot of other contributions by other groups, but one work that I think is in particular critical in the development of this field is the Carbonic group again from 2018. This is work we also contributed to, where there was a nanowire again, but here using the electron and laser to tune over frequencies and show that we can improve the microscopy capabilities. So if you think about the applications we can get through this kind of interaction, we use the laser itself to do spectroscopy of the response of the system with milli-electron volt resolution. This is something that electron microscopes in the past were never able to do because the electron energy resolution was not high enough. Even with the best systems like the TEMIS and the Technion, we cannot get to resolutions of that type. And the lasers can have that and do much more than this. Now, more recently, measured in 2019 and published a few months ago, is our work on coherent electron interactions, where we see cavity dynamics, photonic cavity dynamics. We imaging photonic crystal cavities, and in parallel with us, back-to-back work. This is the work led by Ofer Kfir, and from the Ropos group. There's also a PhD student here. Also looking into cavity dynamics in very different structures. We looked into whisper and gallery modes. We published those recently back-to-back. And now we're looking into a lot of more exciting things. And I want to show you one thing that we're now working on analyzing before I finish. I don't think I have much time left. This Cherenkov work opened a lot of doors for us because it allows us to study a lot of different interactions that are related to grazing angle interactions. Those are the kind of things that happen typically in free electron lasers or in electron accelerators. And for this, we are now putting in a structure that is going to be designed as a particle accelerator. And this community has I think is now led by groups in Stanford, in SLAC, and by another group in Germany. This is a Homolov group. Some of the theory that really started this field was done by Levi Schechter and the Technion. I learned about it as an undergrad. But what we are trying to do now is see what kind of quantum physics has to be used to see the dynamics there. And that is the kind of thing that the Stanford group is now leading. How do you design accelerators on the scale that is very small? So those will be photonic, nanophotonic accelerators that will be very efficient in having energy transferred into the electrons. They call it A-chip, accelerators on chip. It's designed on silicon photonic structures, so that's silicon photonic elements. A student who is now leading the analysis of this is Yuval Adiv, a master student in the group. Now, what we saw there is that we got a setup that is made from silicon from the group guys in SLAC. This is a grading structure that is designed to effectively, efficiently couple in a laser light that comes from the side, and then create a near field that is strong enough to transfer energy to the electrons. You can also, by the way, hear the talk that Yuval gave on this in Clio. It's still recorded online, and is giving much more information. You see, those are the first structures we worked with. So you can see a mesa here where the electrons can interact with more effectively, and the grading structure on top, designed for the energies we're working with. This is a 90 microns long mesa, so it's slightly shorter than the interaction we did in the Cherenkov experiment. And what I want to stress as one point here is that you can use the same theory we developed for the Cherenkov experiment, and now focus on the part here that is the electron energy distribution that is using the Pinham theory for it. This is again the Bessa functions from before, and compare it to what's done in the classical electron accelerators community, for which you can replace the same element here, what we call the raw coherent, with a raw classical. That's the distribution of electron energy change, and put here a formula that looks like this inverted square root. When you do that, you just replace this expression by that one, replace a discrete set of harmonics here to a continuous spectrum. You get exactly the results that are predicted by the classical physics result scenario. And of course, there are some approximations here. One of them is paraxial. The other one is that the electron doesn't change its energy by too much during the interaction, because then it will do something that is called slip off. It will slip from the phase of the laser. It will accelerate while it's moving. And for that, a much more advanced theory has to be developed in the classical side, and it's done. It's done for many years. And for the quantum case, we don't know what happens yet. There is no theory for this complete scenario. Yeah, it has to involve more advanced solutions to the Schrödinger equation for that case. I think it's a really cool example of the classical quantum correspondence that we see here in regimes where we don't yet know what will happen in quantum mechanically. And we are hoping to get to those regimes exactly in the next few experiments. You can see, for example, how this looks like in an experiment. This is the electron energy distribution again. The classical picture will give us a continuous curve here, but the quantum one gives us those discrete peaks. So we see the quantization of the interaction with the electron happening there. And that's one example of recent fitting that Yuval did, and I think we're working now on improving it further. And with this, I think I'll wrap up by saying that there is a lot of more stuff we can do with those systems. We saw that the key element to understanding the quantum nature here is that we have to think about the photons as being dressed by the optical environment. We think about the electromagnetic field as being modified by the optical environment. This is critical to explain the experiment classically, but it's becoming even more important when we start thinking about it quantum mechanically. And that's something that the community is now going into. How do we describe effects of single photon interactions and not just laser fields interacting with the environment? And for that, the theory of microscopic quantum electrodynamics is becoming key. The grazing angle conditions is really stuff that was experimentally the hardest to achieve for this experiment. And we observed through this quantized stimulated radiation and also acceleration at record efficiency. It is not a record interaction strength or acceleration in any way. For that, a much stronger lasers needs to be used, and our system is not optimized for strong lasers, but it is definitely, in terms of efficiency, the longest interaction that can be achieved in those energies. And it's creating free electron columns, which are interesting on their own, and we can talk a lot about what you can do with them. And I think the most exciting fundamental part of it is that the interaction depends on the electron quantum wave function. And that's something that is more, has much more implications and is interesting to discuss further. But I don't think I have time to say much more, just that we did more experiments since then. I only mentioned very briefly the one we had in Nature recently. This is interesting for me from a fundamental perspective for thinking about the collapse of the electron wave function during that interaction. And why is it that in some cases we see the electron function behaving as a quantum wave function for the interaction here? So we have to think about it as a psi. But for other effects that we do in the same setup, when we look at the radiation emission from those electrons, we actually have to treat them as collapsing before interacting with the field in order to explain them. That kind of scenario where in the same experimental setup we see one effect that requires a collapse of the wave function and another one that requires keeping it coherent is a peculiar question that and we have a lot to say about this, but this will be a whole separate discussion to do. So I think I'll stop here, and I'm glad to take questions. I'm glad for people joining.
Okay, thank you, Ido, for an interesting talk, and the floor is now open to questions. If people want, people can unmute themselves and go ahead. So
it's much harder in Zoom normally, right?
If there's no,
I have a quick question. You mentioned
okay.
at the beginning a comment, I think by Landau, that the phenomenon, the quantum phenomenon, was a very minor difference. In what you do you observe bigger differences, or just you're able to observe those small differences more accurately?
So the comment by Landau was thinking about the energy difference that we see in those discrete peaks. If you look at the numbers, the energy difference that we have in absorbing one photon is about 1 electron volt. We see changes of something like 1 electron volt. It's a typical order of magnitude. While the electron energy, the same electron that does the interaction, carries an energy of a little bit more than 200 kilo electron volts. So we're talking about a bit more than 5 orders of magnitude difference. So the single photon has an energy of 1 eV, while the electron has more than 5 orders of magnitude more than that. And that difference is the reason for neglecting those kinds of corrections, at least in the Cherenkov experiment and in the response by Landau. I think that the fact that we can measure changes so small, that is what happens with those modern detectors, the electron energy spectrometers, is the way to see the quantum behavior there. And that's the thing that potentially Landau didn't take into account. Although I can find other ways, even without those detectors, to go around it and still find corrections of that type. And we talk about in theory papers. Experimentally, the only evidence breaking from what he expected is through this measurement tool. And I think that in the future, we'll see other places where it breaks.
Hi. This is Yiming. Hi, Ido. I have I have two questions. One is actually related to the data. One is the you see in the energy spectrum there is a curve. It's like a Gaussian. In the envelope, you average that and show the oscillation at the quantum part. That's the oscillation have a h bar omega, the spacing. Give you the quantum. My question, the first,
or in a
there's the envelope, right? The envelope is a Gaussian, some kind of Gaussian envelope.
Let me explain this in 2 sentences. There is a mixture here of a coherent interaction that is just a Bessel function in behavior, and that doesn't have a Gaussian function. It's much more complex, mixed with incoherent parts, because the electron pulse duration is often longer than the laser pulse duration, so you actually have to mix the interactions, and that's the reason we convolve it with some density matrices. with some density.
My question is there some way to really remove the incoherent part? I mean, to make your electron beam more coherently, so it really looks like a single identical electron always do the interaction. Then you can get much stronger signal in your spectrum. But now the incoherent part give you this envelope. You need to remove it, right? So is there a way to improve your electron beams to get better coherence?
So it's if we want to get the clean theory part without having to do those convolutions and all that stuff that we do to fit the experiment, you want to have the electron see an effectively plane wave photon. That means the electron pulse duration has to be shorter than the laser pulse duration. There are two ways to do that. Either we make the electron pulse duration shorter than about 200 femtoseconds. No one knows how to do that right now. And it's an interesting question in the community. It looks like there is some uncertainty principle that blocks it. But that's a topic to discuss. The other option is to make the laser pulse longer, which will get what you want, and we did that. And we see beautiful results that match the clean theory as well. The price, though, is that you make the laser pulse longer, so you have less intensity. And that's why we don't like to do that most of the time. But some experiments, we still do that.
Yeah, that's the trade-off. Another one is the experiment. The spectrum is little on symmetry. You know. We talked it before. Have you tried to make it, these two banners to change the phase to make it? It's always in the loss part and the gain part, or you can change.
You should solve this. You should. I mean, we don't know. To be fair, there are in the paper we wrote. There are some 5 or 6 reasons this can be, and I have to say that we were very certain that one of them is right. We still wrote all, and now we are very certain that one of them is right, but not the same one anymore. So. You see this asymmetry here as well, and we see this even more strongly in the triangle experiment. This could be because of the long interaction duration, when the electron starts changing its dynamics, its velocity, while it interacts. That is an effect that is captured in the classical description of accelerator physics, and it's critical there. And we don't take it into account, and we have to find a way to do that properly in the quantum picture. So it could be the reason, but I don't promise that this is the reason.
Thank you. Thank you.
Are there any additional questions from the audience? It seems there are none. So I would like to thank Ido for a very nice talk. And thank you all. And I hope we'll see you again on the future quantum seminars. So have a good afternoon, all of you.
Thanks.